So we had begun talking about code generation for tree-address code generation for functions. And in terms of the big picture, we'll generate tree-address code for the body. At this point, we've done semantic analysis, so we know types and so on. So when we do tree-address code generation, what are the kinds of things we need to do? We know what the operations are. We will be flattening out expressions in the process of tree-address code generation. By flattening it, I mean if you have expressions that have multiple operators, they get flattened out into a series of tree-address instructions, each of which has at most one operator on the right-hand side. In order to do that, we need to introduce temporaries that will hold the values of these operations, right, until they can be used. The amount of space that will be necessary for a temporary, and therefore the amount of space that will be necessary for a function, for the function stack frame, that in general is dependent on the architecture. And that's something that comes into play at final code generation time. Fortunately, at intermediate code generation time, we don't have to make that decision quite yet. Temps get stuck into the symbol table, the local symbol table. And your tree-address instructions actually still point into the symbol table. Okay, so we looked at the structure of a tree-address instruction. It's your basic C struct. You have a field that indicates what type of operation it is, what type of instruction it is, an add or a subtract or a conditional on greater than or whatever, right? And you have the operand fields, and the operand fields will typically point into the symbol table. For your implementation, I need to be a little bit more specific, okay? In general, an operand field can be a variable or it can be a constant. So if all you have is a bit pattern, you don't know whether that's a variable or a constant. So you need one bit somewhere to indicate whether that's a symbol table pointer or a constant. Okay, so just keep that in mind. So now we're going to talk about generating code for a function. The first instruction in a function is an enter instruction that points to the function symbol table, right? The assembly code that will be generated from the enter instruction is the code that is necessary for setting up the stack frame. So essentially finishing off the calling sequence, that instructions that belong in the body of the callee. Set up the stack frame, save any state that's necessary, save the return address and so on, and then start executing the body. In order to set up the stack frame, I need to know how big the stack frame needs to be. I won't know that until I've actually generated code for the body. That's okay, because I won't translate this enter instruction into assembly code until after I've seen the code for the body. Okay? This part makes sense to everyone? Okay. So then, followed by, after enter, we followed that by the code for the function body, which is a bunch of instructions. Remember, in your source program, when you enter a function, you begin with the formals and the local variable declarations. So there's a bunch of declarations, right? But what's happening is those declarations are going into the symbol table. They aren't generating code, okay? In C++, you don't have initialization statements alongside declarations. If you did, that would generate code, but what you would want to do is pull those out, pull the initialization out, and make it sort of something, that's a code sequence that happens at the beginning of the function body, right? It's not, the declarations simply say, here are the variables I'm going to use in this function, and they correspond to changes to the symbol table. I generate code for the function body. We saw examples of code gen statement last time, but we'll see it in a lot more detail today. And then any return in the body, including, there might be an implicit return where you fall off the end of the function. There's a return there. So any return is translated to the return sequence. So just as enter F corresponds to the callee's portion of the calling sequence instructions, return statements correspond to the callee's portion of the return sequence, which is set up the return value, put it someplace, deallocate the stack frame, go back to the caller. So for our purposes, the intermediate code level, we'll have leave and returning. Okay? So now let's talk about the actual code generation for the body of the function. We have 75 minutes. We can talk about, we can do a lot of code generation. So we'll begin with simple expressions. Okay, so this is of course going backwards because your project, you're going to be going outside and you'll generate code for your milestone 1 is the entire function, all just the function. And once you've gotten the external function part done, you'll do the body. But let's go backwards, why not? So you have implemented or will soon implement syntax trees. So what do syntax trees have now? Syntax tree nodes for expressions augmented with a couple of fields, 3 fields. There's a type. What is the type of the expression once it has been evaluated? If you did syntax trees as part of type checking, then it has that field already, right? The difference between the node type and the expression type is that if I have an expression that looks like this, so suppose my expression is, let's say, x plus y. My syntax tree looks like this. And this, of course, is a pointer to the symbol table entry. Now, I have over here node type equals some indication of what operation I'm going to execute over there, what code I need to generate for that. And in this case, the code is going to be some sort of an addition operation. And I'm going to have an expression type. And that expression type says, what is the type of the value that is computed once I have carried out the instruction, carried out the operation? In this case, perhaps the value is an int. And presumably, that's the one that you use for type checking. That's what you will use for allocating space for the temporary, if that is needed. This is the one that you'll use for generating the instruction. Okay? I'm also going to have a new field called code, which is the list of instructions that I need to evaluate that expression. Okay, so each expression will have associated with it a list of instructions, of 3 address instructions. We talked about this briefly. Today's Wednesday. We talked about this briefly on Monday, okay, where we're doing a post-order traversal of the tree. So when I'm at a node, I do a post-order traversal, so I visit my children. When I return from those traversals, I have a list of instructions for each child. And then my job at my node is to generate any additional instructions corresponding to the operations at my node, and then glue together the instructions for my children to a bigger list that's now associated with my node, and that's what I send back up to my parent. Okay? So that once I'm done traversing the entire function body, and we do this recursive, post-order traversal, traverse the children, and as I traverse back up, I get, I glue together all these different code fragments, and I get bigger and bigger instruction sequence until by the time I get back to the top, I'm done traversing the entire function body. I have a sequence of instructions for the entire function body. That's what I then traverse to spit out assembly code. And just going way back to something we talked about briefly on Monday, now I have a sequence of 3 address instructions. Now we can expand those out to generate final code. That expansion process in our case is fairly simple. Okay. And oh, I know, there's a final component. There's a place field for each expression node. And that indicates where the value of that expression will live when the program is executed. So I come over here. So I have expression type, node type. There's a there's a code field, and there's a place field. So just quick preview of what's going to be coming. The code field points to a list of instructions. These are instructions. A list of instructions that will evaluate this expression. And in this case, it might look, this is a small expression, so it'll look like a single instruction that says add x to y. The place field is it indicates where the value of this expression will be computed at runtime. Where is the value of this expression going to be found? What I'm going to do for this is I'm going to create a temporary, stick it in the symbol table, and point to the symbol table entry for temporary that holds result. Okay? Yeah, Ryan.
You're talking about putting variables in memory, but is there any place where we're just going to use registers? Or is that not?
So the question is, I'm talking about putting variables in memory. Will we be using registers? For our assignment, for our project, we'll be using registers in a very, very limited kind of way. The MIPS is a load store architecture, so we'll load values to memory into registers, do the computation, and store them right back. Okay, so their permanent home is going to be in memory. That's not a great way to manage hardware resources. You would do much better if you, in terms of performance, if you actually used registers more intelligently. And we could, but that means more work. So one thought that has crossed my mind is, given the vast amounts of discontent I have encountered about the week after Thanksgiving, there being no assignment, people have expressed their dissatisfaction with the state of affairs in loud and vociferous terms and said, we cannot go by so many days without writing code under tight deadlines. What? Don't look at me, I didn't say it. Anyway, so I had thought about having a reasonable assignment that didn't have a huge learning curve, that could be done in that time frame, that would have educational value. And so here are some of the things that I considered. One would be to do something like write a linker, which is sort of the very back end of a compiler, that you bring your .o files together and create an executable, or actually compile to machine code. That has enough of a learning curve that it didn't seem appealing. Okay, there's a lot of niggly little details to take care of, and in terms of the effort involved versus the amount learned, I didn't know that it was worth it. We'll be talking about linking in the class, but it's a fair amount of work. Like I said, there's a whole bunch of really niggly details that need to be dealt with. So the other thing that I thought about was some sort of optimization. And the most obvious one that comes to mind is register allocation. Okay? The basic code generation that we're talking about, like I just said, is that everything lives in memory. You load them into registers. When you need to, you use them in registers, then you put them back into memory. The MIPS is a load store architecture. You need to do that for arithmetic anyway. The problem that I have, and I haven't figured out a solution to this, is that if and when you do register allocation, SPIM doesn't give me statistics that would allow you or me to figure out how effective your register allocation is being. Right? So I haven't quite figured that one out. It's like, okay, let's say you do register allocation. How do I evaluate your code in a reasonable way? So I need to think about it. But I would encourage you to think about it too and see if you have any suggestions. Now, like I sympathize with you. I know it's difficult to go that many days without a hard code deadline. So, you do what we can. So going back to evaluating expressions. So we have this place field for each node in an expression syntax tree. For intermediate code generation, this place field will simply refer to a symbol table entry for a temporary that holds the value. That's, as I illustrated over there. The place field for that plus node just points to a temp. And then at final code generation time, this is mapped to an actual memory location. Now I'm going to be talking about code generation for expressions first. And what I'd remind you again, this is really, really important to keep in mind, is that we're talking about expressions, but we are generating code to evaluate the expressions. We aren't actually evaluating the expressions. It's a very natural reaction to see x plus y and say, oh, I need to add x and y. No, you need to generate code to add x and y. Okay? All right, let's do some simple ones. The expression is an integer constant. It's a leaf node. So what do? You don't do much. Okay? So we'll keep things simple. I'll generate an instruction that says, take this integer constant and load it into this temporary. All right? So I need a temporary for that. So e.place is a new temp, and e.type. Remember, new temp is a function that takes a type as an argument, creates a temporary of that type, which means creates a symbol table entry that has that type, and sticks it in. And then I simply produce the instruction e.place is assigned that the value of that integer constant. If I have an identifier, so this is a variable, and remember by this point we've finished type checking, so we know that this is something that I can assign to, right? Or I can take the value of. This is an identifier that's of the appropriate type. So code generating for this expression is, well, if it's an identifier, it's got to live someplace. There is a symbol table entry for that identifier already. There must be, right? We've done type checking, so this must have been declared previously, etc. So there is already a place where the value of this expression lives. I don't need to do anything more, so I don't generate any code for it. Its values wherever that location, the location for that variable is. Okay? Everyone okay with this? Let's do some simple expressions. Unary minus. So what do? This guy's node type is unary minus. Well, again, post-order traversal, right? Traverse the children, generate code, come back up, generate code for me. So I generate code recursively for E1. So now I have, when that returns, what do I have? I've associated with E1 a place node, which is possibly a temp, possibly a variable, but it's a symbol table entry where the value of E1 will live at runtime when E1 is evaluated. Okay? So let's say it's a temp. That means that when I start doing final code generation, that temp will be assigned some memory location. That memory location is where the value of that expression will live. If it's an identifier, then that identifier has a symbol table entry. It will be assigned location when we start doing final code generation. At runtime, that location is where the value of that identifier will live. So there's a place field for this subtree. There is also a code field, like here, which is the list of 3 address instructions which, when executed, will evaluate this expression. So I have an instruction sequence to evaluate E1. To take the unary minus, I create a new instruction, which is a new 3 address instruction whose operation is U minus. And what location does that U minus operation operate on? I apply this operation to that location, E1.place. What's E1.place? It's the location where this guy's value lives. Okay? So I'm creating an instruction that says take whatever value is at this location, apply a unary minus operation to it, and put the result in this location. E dot place is a new temporary that holds this guy's value. Yeah, John.
Is place just a pointer to the location on the syntax tree?
Place is a location where the value of the expression will be kept. At this point, it's a symbol table entry.
So it's just a pointer to that symbol table entry.
So I recursively traverse and generate code for E1. I create a place to hold the value of E. This recursive traversal has created a place to hold the value of E1 if necessary. Or if it's just a variable, then that's already there. So the code that I generate is whatever code evaluates E1 followed by a unary minus operation applied to the runtime value of E1. And the destination is this guy's place. Okay? So this is the one thing that potentially is the most confusing. So let's spend a little bit of time making certain we understand this, and then the other parts will be much easier. Keith.
So the E1.place is basically saying, like to the parent, whoever needs that, this is the temporary that was used to figure this out. So use that temporary in your.
That's exactly right. E1.place is a temp or a symbol table entry where the value of E1 will be kept at runtime when the expression is being evaluated. So at runtime, what will happen is, let's imagine evaluating this whole expression E. This whole expression E has a code sequence which consists of the code for E1 followed by this instruction. Okay, so this circle plus thing means concatenation of sequences. Okay, so the code for E is the code for E1 followed by this unary minus. So when I execute the code for E1, that will, no matter how complicated E1 is, this recursive traversal says that when I'm done, when I get this code for E1 and I execute that code at runtime, that will evaluate E1 and it'll compute the value of E1 into that location, wherever that location is. Okay? Now, at this point, we don't know exactly where that location is. We know it'll be somewhere in memory. Where it is, we haven't figured out yet. Okay? All we know is that we've allocated a symbol table entry for it. Now, depending on how smart my compiler is, maybe it'll say, you know what, that location doesn't even have to be in memory. I'll just keep it in a register or something. Some location, we'll worry about that later. Okay? But it is a location. The correctness of the compiler, which we hope it's correct. Of course, your compilers are correct, right?
Yeah.
Yes. So the correctness of the compiler says that this will appropriately evaluate E1, put the result of that into E1.place, this location. So then I simply take that result, apply a unary minus operation on it, and put the result into E.place, which is this new temporary. So that's the value of E. So this is the code sequence which will evaluate this whole thing and put the result into that location. So now my parent, this guy's parent, can operate on E.place and do whatever operations are necessary. Okay? That good? You don't look happy. You don't look happy. Okay. Maybe it's too early in the morning. Let's talk about a binary addition. So my expression E is a plus node with two children, E1 and E2. Post-order traversal, I traverse E1, I traverse E2. Those evaluations come back. What do I have? I have the code for E1 and a place for E1. I have the code for E2 and a place for E2. So I'm going to evaluate E1 and E2, and then I'm going to take those values, I'm going to add them, and I need to put that result, I need to put the sum into some location. I need a place to hold that sum. So I'm going to create a new temporary. So that's E dot place. That's where the value of this whole sum is going to go. Okay? So now, what is the code? What is the instruction sequence that will cause this whole thing to be evaluated? That instruction sequence is going to consist of the following. It'll be some instruction sequence to evaluate E1, some instruction sequence to evaluate E2, and then an add instruction. Okay, this is way too quiet. Okay, I don't like this. I need you guys to ask me questions, because I refuse to believe that I'm explaining it so well that it's all crystal clear and there are no questions necessary. So I refuse to go forward. I'll go over this one more time, and then I refuse to go forward until I have some questions. Steve, thank you.
I guess, going back a little bit, what was the place location? Is that something as simple as, when you malloc, you get a memory location, pass that memory location as the place?
So the question has to do with, what is this place thing? And that's something that really does confuse people. That's in my experience, which is why I'm a little alarmed that no one's saying anything. That's a bad sign. What's happening? So let's kind of step way back and think about what's going on over here. We're talking about evaluating expressions, but we aren't really evaluating expressions. We are generating code that, when executed, will evaluate expressions. Okay, so this one additional level of indirection confuses the heck out of people. If you think about, okay, you guys have written plenty of code. You've debugged plenty of code. Well, Brian hasn't, he says. He shakes his head. But other than that, if you think of, well, in 352, for example, we've talked about stack frames and dangling references and such like. Suppose I have an expression x plus y, and let's suppose that they're local variables in a function. Where do they live? No, someone else. The silent majority. What about the stack? What's that? They live in the function stack frame. Okay, so someone has to figure out where in the stack frame they live, right? So, and obviously it's the compiler. GCC takes your source program that has this expression in it and puts it somewhere in the stack frame for that function. So think about what GCC is doing. And you guys have seen this happening, though not quite as intimately as we'll be getting into here. But you guys have seen this happening. You execute code, and when you see this happening in the debugger, you know that x and y live in the stack frame for the function because they're locals. And you know that because if I return a pointer to a local variable and then the function returns and I'm still using the pointer, Valgrind will complain loudly, right? Oh, you're using a deallocated memory location and so on. So GCC, the compiler, puts x and y into the stack frame, and it generates code to access those memory locations in the stack frame when appropriate, retrieve from those memory locations, do the additions, store back into the memory locations. Okay? So what the compiler has done, what GCC has done, and you can actually look at that if you do a GCC-big S, you can see the assembly code that comes out. What GCC is doing is it is creating code which, when executed at runtime, will cause x plus y to become evaluated. So that's what we are talking about over here. So one of the things that GCC needs to do is to say, okay, this variable x is going to occupy some 4 bytes or whatever in the stack frame, okay, a specific memory location, in this case a specific memory word. And y will occupy some other specific memory word. So the compiler is making decisions about where in memory these variables will live. And the code that it generates, the code to actually retrieve those the values of those memory locations, do the addition, put the result back into some other memory location perhaps, those decisions rather the code that is generated will depend on where exactly in memory these have been placed. Because the code that is generated has to refer to those memory locations, right? Okay, so the compiler, and your compiler will do this, the compiler is making decisions about where in memory, where in the stack frame, or if it's a global, where in global memory, where in memory each variable is going to be placed. That's what the place attribute is about, this place field. That's what this thing is about. So we are making this decision in 2 stages. At this point, because we are doing intermediate code generation, remember intermediate code is machine independent. Okay, it's real close to the machine, so we've come pretty low level, but it's still not machine specific. So what we're doing at this point is saying, I need to allocate some memory location for this result. I have to remember that. I have to remember that I have to make the decision. But I won't make the actual final decision about, stack frame slot 16 or stack frame slot 23 or whatever. I won't make that actual decision until final code generation time. For now, I will just remember that I need to allocate space. So I will call new temp, and what new temp will do is it'll say, oh, you need a new temporary. You need space for a temporary. Sure, I can do that. I'll create a symbol table entry. So new temp will create a symbol table entry for a new temporary, and it'll give back a pointer to that symbol table entry. So the code generator will simply use the pointer to the symbol table entry. At final code generation time, we'll take that symbol table entry, and we will say, this symbol table entry will live at memory location 12 in the stack frame, or whatever. So that's how the mapping between variables or intermediate results and actual memory locations in the frame will be set up. John?
But while you're creating this, though, if you're going to be pointing to the symbol table entry, if it's local scope, though, isn't it just going to get sort of wiped out, the pointer address?
That's a good question. If it's a local scope, then it will get wiped out when the function returns. Right. Okay? But by the time the function returns, hopefully the value has been computed.
Oh, okay.
So again, let's keep in mind the distinction between what's happening at compile time and what will happen at runtime. So at compile time, what I'm saying is, here's the code that I'm going to generate. The code that I generate looks like do stuff, allocate a stack frame, save the return address, and so on, generate code for the body, which will include stuff like, generating code for the body will traverse the expressions and such. That will cause temps for the body expressions to be created, which will cause space to be allocated in the stack frame. Right? Now, when I'm allocating space in the stack frame, how am I actually doing that? I traverse the body of the function, including all of the expressions and all of the statements. And whenever I need to, I call new temp, and that sticks a temporary in the symbol table. Okay? With me so far?
I'm just thinking of like other cases where it's like it's referencing a function, say out like past yes.
Let's just work through this, and then we'll come to that. Okay, so let's just work through this. So I traverse the body, and let's suppose the body is simple, because I only write simple code. So we have simple little dinky expressions and such, and I traverse them, and I stick a bunch of things in the symbol table. Then, so far I have not allocated any space at all, right? I'm just sticking stuff into the symbol table. Then I'm done processing the body. Now it is time to generate final code for this function. In fact, if I step way back, the big picture is process the program a function at a time. Read in the function, do syntax checking, do type checking, do syntax reconstruction, do 3 address code generation, allocate space, do final code generation, then throw it all away, do the next function. Okay, so we're processing these things a function at a time. I will traverse the body, stick all of that stuff in the symbol table. Then I'm going to do final code generation. So now I come back and I say, okay, I need to allocate a stack frame. How much space do I need? Well, I have traversed the entire function body. I've looked at the entire function body, all of the expressions. I have created all the temps that I'm going to need. So I can traverse the local symbol table, the function's local symbol table, and I can just calculate how much space I need, because I know how big each symbol table entry is going to be. How do I know that? How do I know how big a symbol table entry needs to be? No. No. Come on, folks. This is something that I'm sure you know the answer to. I know you're being shy. There's no need to be shy. Because, no, I haven't defined a thing. I'm sorry, say that again?
You have the type of the symbol.
I have my, absolutely, exactly. I have the types in the symbol table. Between the language and the architecture, these two things together tell me how much space I need for each type. Good, excellent, thank you. Yeah, so that symbol table information tells me how much stack frame I need. Therefore, I can set up the allocation, the stack frame allocation. Then, since I know how big the stack frame is going to be, again, I can just walk down the symbol table. And depending on the structure of the symbol table, it's a hash table or it's a linked list or whatever. Walk down the symbol table, assign offsets in the stack frame to each variable that you need that's in there, variables and temporaries, and we're good to go. Keith?
Since we're seeing the temporaries only really in the expressions, does that mean that every temporary is going to be the same size because chars will have to be sign extended to fit more?
Does that mean every temporary will be the same size? Chars will need to be sign extended. Yes, it does.
Okay.
Yes, it does. But that's because we have a very, very simple type system. If you had, longs and long longs and doubles, then temps might be of different sizes. Diana.
So every time you evaluate an expression and create a temporary or create a place in the symbol table to put your result, do you then put a pointer tag on that expression pointing to the symbol table, and that way you can move up and access or
So the question is, when I evaluate a symbol table, I create a place for the result of that expression. Would I put a pointer to it? Yes, I do actually, and that is this place field, that guy. So the syntax tree node for the expression now has this new field added to it, which says, oh, by the way, when you're done, this pointer is where the location is the location where the value of this expression will be found at runtime. Okay? So the code generation here, this is what it looks like, and really the code that you would write or I would write is not that different. This is a little bit abstracted, but it's pretty close to the real thing. So recursive traversal, traverse E1, traverse E2, create a new temp. And then the code for this whole thing consists of the code to evaluate E1, followed by the code to evaluate E2, followed by a new instruction which will add the results. And because this is a compiler, we're simply generating code. That code, when executed, will actually perform the addition. So this instruction to create the sum says apply the plus operation to this location and this location at runtime to the value of E1 and the value of E2, and whatever the result is, put it in E.place. E.place is where this guy's value lives. Okay? Yeah?
Is it possible to go back one slide?
Sure.
For the identifier syntax tree node, I'm a little confused why we don't really seem to do much of anything right there.
The reason we don't do anything for identifier is that we like identifiers. Sorry, I'm being facetious. The reason we don't is that this guy already has a location it will have a location because there is already a symbol table entry for it. So where does the value of this identifier live? Let's say the identifier is x. Well, we will allocate space for x somewhere in the stack frame. So there is a symbol table entry. So I don't need to allocate a separate instruction. I'm sorry, I don't need to allocate a separate temporary to hold the value of x because the value of x is in the location for x. Okay?
That's okay.
Okay.
Not the code part.
Since I know where the value of this expression is, I don't need to do anything else to compute the expression. Its value is right there at runtime. Its value is right there, right? So I don't need to do anything for it.
I think I'm thinking down towards final code where we have to
Mhm.
load it, and I was thinking
Mhm.
we have to have something, but this is just intermediate representation.
This is just intermediate representation.
Thank you.
Okay?